Okay, we're going to do 9.4, 9.5, 9.6. 9.4, volume. Huh? Oh, lights. So we can see better. Okay, 9.4 is volume. That is telling you how many cubic things you can fit. Like if you have a box like this, how many cubes are stacked there? That's what volume is. How much something holds inside it. Like how many cubic feet of water, cubic inches of water, or whatever. Okay? That's what volume is. So to do volume, bless you. I need to do it different, sorry. Okay, to do volume you need the length, the width, and the height. Because you're doing how high something is also. The volume of a rectangular prism, that's what this is, a rectangular prism, is length times width times height. And that'll tell you how many cubes it will hold. So I wonder what our unit will be in. If these were inches, it will be in cubic inches. Okay? So if you have a cube that is 2 by 3 by 5, the volume of that cube, let's say that was centimeters, the volume of that cube will be 2 centimeters times 3 centimeters times 5 centimeters. So we got 2 times 3 is 6 times 5, which is 30. See, we have centimeters 3 times. 30 cubic centimeters, like that. Okay? That's the easiest one. They aren't that hard, but that's the easiest one. Let's say we have, you know what this is called when it looks like a Coke can? Or like part of a car? Like a cylinder on a car? Mm-hmm. The shape is called a cylinder. Okay? It's round on the top and bottom, and it can be, this is the height, how high it is from the bottom to the top. Okay? For the volume of a cylinder, just find out the volume of how much your Coke can hold. They do, all volumes are how big your base is times how high it goes. See, the base of this was 2 by 3, wasn't it? 2 times 3, the height was 5. That's the base times how high it went. The base of this is a circle. So we need the area of a circle for the base, which is, what was the area of a circle?
Pi r squared.
Pi r squared. Pi is squared. Scared. Okay. Pi r squared times the height. So the volume of a cylinder is pi r squared times the height. So you have to have the radius of that circle. You have to have the radius, and you have to know how high it is. And that's all the stuff you need right there. So even if you have a cylinder that doesn't go straight up, that would be unlike a cylinder in a car. You still use the same formula, but the height is going to go from here to here. Your height will be over here instead of the length of this. You'll be using this height and the radius of your circles to plug in here. Okay? If you have a sphere, you know what a sphere is? It's like a ball. It's like the earth, a globe. This is a sphere. Okay? The volume, how much it will hold, the volume of a sphere is 4/3 times pi r cubed. Okay? This isn't 3/4. Don't turn it into 0.75. That's not 3/4. It's 4/3. That'd be 1 1/3. It's easier just to leave it like this and do 4 times the 3.14 times the radius 3 times, and then after you're done, divide by 3. That's how you do the 4/3. 4 times pi times radius times radius times radius, and then divide by 3. Okay, there's another shape. And what does that look like? Looks like, yeah. It looks like ice cream cone, right? That's why it's called a cone. Or maybe that's why an ice cream cone is called a cone, because it's in the shape of a cone. Okay, a cone will have a height that goes from the tip, which is your vertex, and it's going to come straight down at a right angle to your circle down here. This is your height. You're going to need the radius of your circle and the height of the cone. And it looks almost like the, remember our cylinder was pi r squared times the height? That was what our cylinder was? Yeah. It's the same thing, except it's got 1/3 of it. I don't know why that works, but it works. When it's pointed like that, it's 1/3 of what it would be if it went straight up. 1/3 of pi r squared times the height. So what you need is your radius and your height to fill in there. What you can do to figure these out is just do pi times the radius times the radius times the height, and then you could just divide it by 3. Because 1/3 is a repeating 3, is better than putting that on a calculator. A repeating 3, it's better to just divide by 3 at the end. And you just have a lot of those that you have to do. Now let's go into 9.5, angles and triangles. Angles and triangles. Okay, when you have an angle, the tip of the angle is your vertex. Okay, both of these sides come off from the vertex. These are both rays. It's like a ray of light coming out from a flashlight. It has a starting point, but it doesn't have an ending point. These are both rays. Okay? If you have letters, like a dot here and a dot here, your vertex is A. This ray right here, you would write this ray as A, B. It started at A and it keeps going. So this is ray It's written like that, or it could be written as ray AB. So when you say it with the word ray, you put the beginning point as the first letter and then the other letter. So this would be written like this, or AC with the arrow. Okay, the angle, this angle right here, there's a lot of ways to write it. This is not a less than symbol. It's flat on the bottom. This is an angle symbol. Okay, this could be written as angle BAC or angle CAB, or it could just be labeled from its vertex, A. Okay, let me see. What else do we need here? Here's some special angles. Let's say we have one that, like this. Does anybody know what this means? This square right here? That's a 90-degree angle, or a right angle. Same thing. So this right here is a right angle. If you have a small angle that's less than 90 degrees, it's acute angle. Kind of like a little bitty cute one, it's less than 90, acute one. And if you had an angle, see here was 90, it's bigger than 90 degrees. Obtuse. Like obese, big, obtuse angle. There's also a straight line is a straight angle. If it's a line, it's a straight angle. Okay, so that's your types of angles. Let me get a protractor. Okay, to measure angles, just draw an angle on here. What kind of angle is this? Obtuse. It's bigger than 90, right? Okay, if you're going to measure an angle, you have to put this vertex, the point of the angle, it needs to be on that bullseye. I'm not going to get in trouble for saying bullseye, am I? No? Okay. I know politicians get in trouble for bullseyes. I don't know if teachers do. Okay. So you need to put it there. And see this part of it? Even though the dot is there, that's not where you're going to put it. You need to line this line up with the line. So turn it until that line disappears on the line, okay? Now that's lined up. This came out here. Actually, this should line up with a 0. Even though this looks right, this line out here should go through 0. So I need to bring that down just a little bit right there. That looks like it's on a 0 now. See how it's on the line right there? That's 0. See how it goes 10, 20, 30? On this it's like 180, 170, 160. You're going to start from where it's 0. So this one you will read on the outside. Okay? So if you go, I should have made it a little bit longer, but you can read where it goes to, huh? So there was 90, 100, 110, 120. It's almost 125. We'll say that's 124 degrees. See that? So that's like the whole angle right here is 124. Let's make a couple of other angles in here. If you have a little bitty one that you can't read because it's maybe in the book, with a pencil you need to extend that line out where you can read it. Extend this line, this ray, and this ray, so you can read it on your protractor. Okay, we could actually even line it up with that one. So if you want to, you could line it up there. As long as the tip of it's right there, and that goes to a 0. See, this one, if we were reading, we wouldn't do 170, would we? We would go to 10. 10, 20, 30, 40, 50, a little after 55, about 56. So this angle right here is 56 degrees. So you see how to read a protractor? Alrighty. If you have, I don't know if I can make a right angle. Oh, I guess I can. Okay, make a right angle. There's a right angle. Let's say we have two angles in here, angle 1 and angle 2. It'll probably just have a 1 and 2 in there. These two angles add up to 90 degrees. Angle 1 plus angle 2 is 90 degrees. If these two angles add up to 90, they are called complementary. Complementary angles. Okay? Those two angles are complementary. So you could even have 3 angles that add up to 90. I think, let me see, wait a minute, complementary. No, it's only got to be 2, sorry. It's got to be 2 angles that add up to 90 to be complements. Okay, let's do a straight line here. And we'll put 2 angles here. Angle 1 and angle 2. These 2 angles, angle 1 and angle 2, add up to what? 180 degrees, which is a straight line. These 2 angles are supplementary. So if it adds up to 180, they're supplementary. If the 2 angles add up to 90, they're complementary. Okay. It's going to want you to measure some of these angles in your book. See what I've done? I had to extend them. So you either need to copy it onto another sheet of paper and extend it, or you can put it in your book and then erase it, okay? Okay, another thing, if you have a triangle, every single triangle, these, like angle 1, angle 2, and angle 3. All 3 of these angles, when you add them up, add up to 180 degrees. So if you knew, like angle 1 was 60, angle 2 was 50, you could figure out what angle 3 was. Because you know that 1 plus angle 2 plus that third angle are add up to 180. So this much is 110. So what are you going to add to it to get 180? 70, right. Just subtract the 110 from 80 and you'll say angle 3 is 70 degrees. They all add up to 170. There's another way to classify angles other than obtuse, the ones that we said here, right angle, acute, obtuse, straight angle. Okay, not angles. There's a way to classify triangles. The same thing as like we did on the angles. Let's say we have a triangle that's exactly the same on every side. Say it was 3, 3, and 3. This would be called equilateral. Equal angles. That shouldn't be a capital L. This is all one word. Equilateral. This is an equilateral triangle. Okay? If you only have two sides that are the same, like we had 3, 3, and 2. That's called isosceles. Isosceles triangle. ISOS. Got it. Isosceles triangle. And what if they're all different? Okay, say that was 4, 3, and 5. All different. Scaling. Scaling triangle. Okay? This is classifying the angles by their sides. Okay? There's another way to classify triangles by the angles. Remember the cube, obtuse, like I said a minute ago? Okay, if a triangle has an obtuse angle in it, this obtuse angle, that would make this an obtuse triangle. These triangles that I already drew, all three of these have all acute angles. None of them, well, this one might have a 90, I'm not positive. For sure these two right here have all acute angles. So if it has all acute angles, it has to be all of them acute, okay? All acute angles, then it's an acute triangle. This is only, there's only going to be one obtuse angle. Because once you do more than 90, then you can't add more than 90 to get 180, okay? These two have to be less than 90. So one obtuse angle, or all acute triangles for this, or all acute angles. Okay, there's one more kind of triangle here. One more kind of angle we can put in a triangle. That's your right angle. That right angle makes it a right triangle. Okay? If we knew the numbers, we would know whether it was equilateral or isosceles or scaling. So if you could tell what the angles and the sides were, you could classify it both ways. So let's say we have a triangle like this, and we have a 5, and that's probably more like, it's bigger. Let's say it's 8. Okay, by the sides, it says there's 2 the same. I'll tell you how to remember that one. Okay, this equilateral, they're all equal. I looked at the 2 S's here to remember 2 sides are the same for isosceles. Scaling's just all different. So this one had 2 the same, so it's isosceles because of the sides. and the angles, this is more than 90 degrees. So it's isosceles and it's obtuse. So that's the two ways you could classify that one. Let's do one like this. And here's a right angle. Actually, this one could be two different things. If we have these two sides the same and this one different, we still have isosceles, don't we? But because of the angle, this one's not obtuse, it's a right triangle. So this one's isosceles and a right triangle. Okay, let's do 4, 3, and 2, even though it doesn't look like it. Okay, according to the sides, scaling. According to the angle, they're all small, acute. Okay, so that's pretty much all that you're going to be using for the triangles. That's solid 9.5 now. Put that with that. 9.6. Square roots and oops, that should be an A. Pythagorean. That's an N, sorry. Pythagorean theorem, or the Pythagorean theory. Okay, let's start with square roots. I seem to be able to write it better. Square root. Okay, you know that what square is, right? If you have 8 squared, that 2 up there means squared. That means 8 squared, right? What do you do to the 8? Times it by itself, not times 2, right? 8 times 8 is 64, right? Yeah. Okay, to do a square root, we're undoing a square. You know how multiply and divide undo each other? They're opposite operations. Adding and subtracting are opposite operations. Well, if you have something squared and then you square root something, it undoes it. They're opposite operations, just like multiply, divide, add, and subtract. So if we took this answer, the 64 part, if we did a square root of 64, it's asking us, what did we square to get that? What number did we square? 8. We squared 8. And on your calculator, I don't think anybody can find a cheap enough calculator that does not have a square root symbol on it. This one is pretty cheap, but let me see if I can get the light where it even shows it. See that square root symbol? It has one on it. Okay? Some calculators, you hit the number, you would hit the 64 and then hit the square root and it'll give it to you. You don't even have to hit equal. That's usually the cheaper ones. You hit the number and then the square root sign. Okay, but then a lot of them, you'll hit the square root sign first and then hit 64. Okay, this one, the cheap one that I have, you hit 64 first. Okay, can you see it now? You can see it a little bit. When I hit the square root symbol, it goes to 8. You don't hit equals, you just hit the square root. Okay, if you have an expensive one, that's what I do on mine. You need to figure out what to do on yours, okay? The expensive one, you'll probably have to hit square root. If it's not a button all by itself, sometimes you have this little X squared button, and then up above it, there's a square root. Okay, what you have to do to get to square root, you hit the second button, and then you hit your X squared. That gives you a square root up in your display. So in the display, you see that little square root sign. Now hit 64. Okay? But it's just going to show the square root, and then it'll say 64. You're going to have to hit equals. Now it should show 8. So try that, and if you don't have a cheap one, you're going to have to hit a few more symbols there to do it on your calculator. Okay? Does everybody have your calculator figured out? Not yet? Second square root 64.
Which one did you get?
Clear it. Second. X squared 64. Everybody has it figured out? Yeah? Okay, so I want you to try, give me what the square root of 169 is, using your calculator.
13.
Okay. If you don't get 13, you haven't got it figured out yet. Okay, how about square root of 256? 16. You got it figured out now, right? Okay. So you know what a square root is? Okay. They don't all come out exact. Let's say you have square root of 12. 3 point, yeah, it doesn't come out exact on everything, does it? 3.464, whatever, as far as your calculator goes. So it may not always come out whole. Okay, now let's do Pythagorean theory. See if I can write it right this time. Pythagorean theorem. Okay, there's this Greek dude, Pythagoras. He had a lot of time on his hands because he figured out, he was an astronomer, he was a scientist, he was a mathematician. Back then, if they were one, they were a lot of things. Okay, what he did, Pythagoras, he was this Greek dude, you know, the kind with the state laurel leaves on their hair, on their head, way back in the Greek days. Okay, Pythagoras, what he figured out, he played with right triangles. Remember, they have a right angle here? He played with right triangles enough to figured out that every single triangle, this will work on it, okay? First of all, let me tell you what the legs, what these sides are called. The two sides that make up your right angle are called legs. Okay? Looks like somebody's sitting there and their legs are spread out, okay? They're sitting right there. Here's your right angle. Across from your right angle. Okay, across from the right angle, do you know what that's called? Hypotenuse. It's the only place I've seen that word used. You in a right triangle. Hypotenuse is this side across from the right angle. Okay. Now what Pythagoras, I don't know if he labeled it A, B, and C, because he was Greek, he probably labeled it Greek terms, I don't know. We label it A, B, and C. Okay, the two legs are A and B. Now, what he figured out is if you take the length of A and you square it and you add the side B, the other leg squared, it's equal to the hypotenuse squared, the C side squared. You've probably heard that a lot of times, and it's like, if you've never seen it before, you didn't know what it pertained to, this is what it pertains to. A squared plus B squared equals C squared. Okay? If you know two sides of a right triangle, you can find that third side. And so that's what we're going to do. We're going to pick a triangle. I'm going to pick number 32 because it's not one of your homeworks. And it gives us a 4 here and a 4 here, and it wants us to find the hypotenuse. So using this formula, it really doesn't matter which one you call A and which one you call B, okay? Especially in this one, right?
Yeah.
Okay, 4 squared plus 4 squared equals C squared. Remember, squared is not times 2. 4 times 4 is 16, plus 16 equals C squared. 16 plus 16?
32.
32. That's what C squared is. That's not what C is. How do you undo a square? What's the opposite of a square? Remember, multiply, divide, add, subtract. A squared, square root. To undo this, we're going to square root both sides. This undoes that square. So the square root of 32 is how long that side is. That's not a perfect square. It's not going to come out all pretty like you might want it to, okay? That comes out to about, this means approximately, the wiggly lines, to about 5.656 something, okay? It says on the problems you got to do like this to approximate to 3 decimal places. Since we need to go to 3 places, we need to look at the 4th one and see how to round. Since that's an 8, this will be 5.657. Okay, so C is approximately 5.657. And it didn't give units, so you don't have to worry about units. If there's not inches or feet on the problem, you don't have to worry about the unit. Okay, let's do another one, or a few more anyway. Let's do one that has a, let's go 8. This looks longer, but I'm going to make it shorter. 6 and 8. We're going to find C. So let's write A squared plus B squared equals C squared. So A squared is 6 squared. B squared is 8 squared. That's equals C squared. Okay, 6 times 6?
36.
36. 8 times 8?
64.
Equals C squared. 36 plus 64?
100.
To undo a square? Square root. Square root of 100. Yep, 10 times 10 is 100. So that one came out exact. So that was 10. Okay, let's do one where one of the legs is missing. Let's say we know this is 12, and we know this is 15, but we don't know this. And we might as well put an A there, since that's a good letter to put there, since it's usually called side A. A squared plus B squared equals C squared. So we have A squared plus 12 squared. I didn't write the right angle, but it's right there. Equals 15 squared. So A squared plus 12 times 12, 144, equals 15 times 15, 225. Okay, and then how are we going to solve that?
Do the opposite if you subtract.
Opposite of that, subtract 144. So we have A squared on its side by itself. 5 minus 4 is 1. Need to borrow 81.
Yep.
Undoing a square, we're going to do a square root. So A is 9. Okay? Okay, let me go back to one of these we did earlier. Did we do? No, we didn't. Let's do a real simple one with little numbers. A 3 and a 4. Okay? So we have 3 squared plus 4 squared equals C squared. We have 9 plus 16 equals C squared. 9 plus 16? 25. What's the square root of 25?
5.
5. Okay, this is a basic right triangle 3, 4, 5. Okay? If you do multiples of these numbers, look at this one up here. That's 4 times 3 is 12. 5 times 3 is 15. This other side, 3 times 3 is 9. If you have a triangle that says it is 20, 16, and 12, are those the right numbers? Is that a right triangle?
No.
That's times 4, times 4, times 4. Yes, it is. Okay? It doesn't have to be a 3, 4, 5 to be a right triangle, but anytime it is exact multiples of 3, 4, and 5, it will be a right triangle. Okay? It doesn't have to be, but if it is multiples, you know it will be. So you could make up a right triangle just by multiplying every side. Okay, let's do another one here that's not 3, 4, 5. Let's do 5 and 12. That's not one of the 3, 4, 5s. Okay, our A is 12. 12 squared plus 5 squared equals C squared. 12 squared is 144. 5 squared is 25. Add 144 and 25.
169.
169. What's the square root of 169? 13. Okay, that's another one that always comes out to perfect. If you have a 5 and 12 and 13, that comes out. But this is your basic building blocks. What they used to do, the old farmers back in the days, what they would do, using this theory right here, they got a rope and divided it into 12 equal parts. Okay, you have 1 segment, 2 segments, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there's your rope. And what that farmer would do is he would stretch that rope where there would be, well, that's not equal, okay. Where there's like 3 segments here. 1, 2, 3, 4. 4 segments here. How many segments are left over if you have 7 used up? 5 segments. Okay, he'd put this one and this one. If it was a perfect triangle, that 5 would fit exactly up to here. If it didn't quite reach, it was too far down, he'd have to raise that corner up. He'd raise it up until that side met, and when that side exactly met, he knew that was the right triangle. And that's how they cornered off their fields. Like when they were plowing fields and stuff, that's how they cornered them off, where that 5 was going that way. So if you don't have something to tell you exactly what a right angle is, you can use that. Alrighty, I think that's about it. Any questions?